So we can start. So I will start with chapter 9, which are algorithms, and I will go back to VC dimension a bit later because we need algorithms in other courses. We will need neural networks in generative modeling and so on. So we need to do machine learning algorithms also. Okay, so we have to plan in that way. Okay, so I will start with chapter 9, which is linear predictors. Okay, so as the name suggests, linear predictor is about predictors which are linear. So linear, you can think of line or hyperplane and so on. Okay, so so we can define a class of affine functions, let us say. So define a class of affine functions. Okay, so in general, linear is not affine. Okay, I mean linear is affine, but affine is not linear. Okay, in the strict sense. So we define a class of affine functions which are h, w, d, such that w in R d and b in R. Okay, where I define h, w, b, x is equal to inner product of wx plus b, and which is wi xi plus b I equal 1 to d. Okay, so as such, this is nothing but a hyperplane you can think of, and what we have defined are set of hyperplanes. Okay, hwd, d is the dimension of the vector w in then you can think of hyperplane in d dimension. Okay, so d dimensional hyperplane we have defined. So it's a normal form of the plane. Okay, so it's w transpose x plus b, the normal of the plane is w. Okay, so that's the way of defining hyperplane. We have seen this in optimization class as well, and this is just a definition of the inner product. So we are looking into class of affine functions like this. Okay, so basically with this class of affine functions, which are the problems we can let's say do the learning on. Okay, so it could be classification problem, it could be regression problem. So which are the problems we can solve just with these hyperplanes. Okay, so so we will it will be convenient also to use the following notation. So it is convenient to use the notation which is LD is set of all functions that takes x to wx plus b, where w is in Rd and b is in R. So LD is the set of functions. Okay, so here LD is a set of functions where each function is parameterized by the weight w, right, by w, which is a d-dimensional vector, and b is in R. Okay, so we are doing all these repetitions, and b is in R, and each function takes as an input. So each function takes input x, obviously, and returns wx plus b, w transpose x plus b. So what we are saying is that we see this as a set of functions that takes a given x and produces this output wx, w transpose x plus b. Okay, so we can build a different hypothesis classes on, can build different hypothesis classes by doing a composition of these linear functions or affine functions. Okay, in other words, I can compose this with something to get a set of hypothesis class. Okay, so can build different hypothesis classes as compositions of functions which are phi from R to some class y. Okay, so what we are trying to say is that we have collected set of affine functions, but as such they themselves may not be able to decide. We need something more as phi that acts on these functions, and then you make the actual prediction. Let us say y is the set of labels, right? So then you will see the actual prediction. Okay, so for instance, you might have seen, some of you will do a sign of this. Okay, so if you take a sign, then sign will tell you whether the point is on the left side of the hyperplane or the right side of the hyperplane. Okay, but the hyperplane itself is doesn't tell you anything, right? Okay, so for example, in binary classification, phi is a sign function. Sign function is a function that gives you -1 if it's the argument is negative, and it gives you +1 if the argument is positive. Okay, so just to recall, what is a sign function? So sign function is -1 if x is negative, and if it's +1 if x is, let's say, greater than or equal to 0. Okay, so by looking at this, you can already see by now how this will act as a classifier. Okay, so given a set of points and given set of another class, you are looking for a set of affine functions that are like this, and that itself is a predictor. Okay, but that itself was not enough. Just by knowing the line itself is not enough. By knowing this is the hyperplane characterized by W, and by taking the inner product of these guys with this, okay, and making a acute angle or obtuse angle, that decides the point should be classified on the left side or on the right side. Okay, so that's why we need a sign of the of these guy, W transpose X. Okay, so you have you have to take the cosine angle of that, right? And so cosine of the angle, if it's acute angle, then if it's less than 90 degree, so these points are on this side, so they will make less than 90 degree. So then cosine will give you some value, and then if it's on this side, then for greater than 90 degree, you have the negative sign. Okay, and that's why sign is needed. Found a hyperplane, and now for a new test point comes here, you calculate the angle cosine, and if the angle is positive or acute angle, then you say, okay, this is yeah, just to be sure, okay, because I don't remember. So 0, it's 1, right? Cosine, right? So at pi by 2, it's 0, right? And 0, it's 1, right? And this is our pi. So acute angle cosine is positive, right? Acute angle cosine is positive, and obtuse angle, like pi by 2 to pi, it's negative. Okay, so we confirm this. So acute, you will classify it as on one side of the class, let's say negative class or positive class, depending on this angle. Okay, so this is the idea behind linear classifier. Okay, so like I already gave you what is coming, but we will like try to formally put everything, even prove why such classifier will converge and so on. So now to see some minor details. So here we usually call this as a bias, okay, and one of the ways is to clean up this notation, okay, and the way you can clean up this notation is that you also bring this in some form of a inner product, okay, and you can do so by adding an additional 1 in the x, okay, and appending b in w and appending 1 in x. So the modified w, which we again use w again, so ideally it will be w tilde, which is w appended with b, and x tilde where x appended with 1, and then we can write the inner product of w tilde x tilde, and that will be this. So that's a way to kind of like clean things a little bit so that it looks like an inner product. So we will do that now. So it is convenient to incorporate b, call the bias, okay. So incorporate b, call the bias, and into w, because remember that b is also something you are supposed to determine, okay. So unknown is not just w, unknown is b also, okay. So into w as an extra coordinate and add extra coordinate value, add extra coordinate value 1 to x, okay. So that's what we said. So now after doing that, we just write everything as an inner product. So this becomes so then we change w to w1, or in the first itself. So basically it's prepended, so we add in the beginning itself, okay. So w1, w2, wd, and now this becomes our d plus 1, and then we have x prime, which is 1 x1 x2 xd, and this is also in our d. So these are the changes we did. Now with this, our hypothesis w, not the hypothesis but the hyperplane basically. So this becomes, hypothesis will be when I apply the sine function also, right. So composition of sine, then it will be the actual predictor. So this is wx plus b, which is w prime x prime, okay. So in general what we will do is that we will simplify everything and just write like this, wx, okay. From here onwards we will assume that the bias has been added and x is has a prepended by 1. So this is just to simplify things. When it is needed we will look at the bias, okay, but for the moment it's not, okay. So with this linear classifier we will build, let us say, 3 classifiers today, okay. So let us first look into half spaces. So first hypothesis class we will look at is called half spaces. It is designed for binary classification. Okay, and we can think of our features as x and our level space as -1 plus 1. And the class of half spaces are defined as, so it basically carries over from what we said. So we will just apply the sign on LD. Okay, so the space of hyperplane. Okay, so this is sign composed with LD. Now this becomes a classifier. Okay, so set of all x that goes to sign of HWB x such that HWB is in LD. So we made a classifier by composing sign on the hyperplane. Okay. So obviously this hyperplane is parameterized by, so HSD is parameterized by W by the unknown weights W and B obviously, and B in R. So combined unknowns that you have is W and B. Okay, so there are D plus 1 unknowns, and so upon receiving a vector, vector x, it returns a label, the label which is sign of Wx plus b. So basically the label space for us was -1 plus 1, and sign will do that, right? So it will give you either +1 or -1 depending on x is making acute angle with the normal or the obtuse angle. Okay, so to illustrate this in 2D, so in R2 we can have a hyperplane like this, and these are our positive classes and these are our negative classes, and the normal of the hyperplane is like this. So this is our W, and with a calculation we can find out that this point will be 0 minus b by W2. Okay, so W1 x1 plus W2 x2 plus b is equal to 0. That's our hyperplane we are looking for in 2D. So W1 x1 plus W2 x2 is b. So when x1 is 0, right? So when x1 is 0, we want to see where it intersects the y. So when x1 equals to 0, this implies the x2 intercept is, it was plus b equal to 0, the way it is written. So now b will go on the other side, this is minus b by W2. So that seems to be correct, the y-intercept. So the instances that are above the hyperplane make an acute angle. Okay, so it's good to kind of like note all this. The instances above the hyperplane, by above we mean with respect to the W, right? So above means this, not this. Okay, so above is this. So instances above hyperplane make acute angle with W. Okay, and are labeled positively, hence labeled positively. Hence labeled positively, and similarly the other way. Okay, those that make negative obtuse are labeled negatively. Okay, so from the theory that we have, this is the hypothesis class we have, and for learnability, one possibility is that the optimal H, the hypothesis is there right? The optimal H star is there. Okay, so the realizability assumption in this case would be a good one, is that the classes are linearly separable. Okay, so because since I have any hyperplane allowed, as long as they are linearly separable, the realizability assumption is exactly that. Okay, so the points are linearly separable. Okay, so otherwise you cannot, right? That's very evident, right? Because if the points are, if some of the positive classes are like this, and if some of the negative classes, so let us say these are the positive classes, and some came here, and these are the negative classes like this. Now, no matter which affine function you pick, okay, hyperplane, you will never be able to separate. Okay, it is not possible to separate. So the first thing itself is like affine functions cannot separate everything. Okay, so we need a realizability assumption for learnability. In this case, is that the classes we are considering are separable. Okay, linearly separable. Of course, I can fit a nonlinear function, right? So, but then nonlinear is not allowed for the moment, right? So if I have to do like this, then this is a nonlinear. So assuming that all negative classes came here, and these which are on this side of this curve, that I somehow classify as positive. So this could be a nonlinear classifier, but we are not allowed to take that. We are only allowed to have lines. So a realizability assumption is that the classes are linearly separable. Realizability assumptions, linearly separable classes. Okay, so if we want to go in a little bit deeper about how do you characterize those points, then we have to go into something called separating hyperplane theorem. That usually it's done in optimization, but so what you are looking for here in the separating hyperplane theorem, what it says is that suppose you have some certain set of classes like this, and let us say you have, okay, let us say this was the hyperplane, and let us say you have another set of classes which are this. So it builds on some so you do what is called a convex hull of these points. Okay, so we know that the convex hull is a convex set, right? We always a convex set. So what it will do, the convex hull will surely pick these boundaries, okay, and make it like this, like the maximum extent you are going to have, and here for all the negative classes it will build a boundary like this. So you make a convex hull of the positive class, which is a convex set. You make a convex hull of the negative class, which is a convex set. Now these become convex sets A and B. Then the separating hyperplane theorem tells that two non-intersecting convex sets, there necessarily exists a hyperplane, okay, that separates the two. Okay, so that's essentially proving that linear classifier will exist. Okay, so it will not be a linearity classifier. Obviously, we know when the convex hull, I mean, look, convex hull will be a kind of always a convex set, but the problem will be they will, I mean, in some cases they will intersect, right? So for example, in this case, let us say some, when I'm building the convex hull, then let us say some positive classes spilled over here, and I know that there is no linear separability, and this does also violate the separating hyperplane theorem, because if I form a convex hull, then the convex set is like this, and this is the convex hull, so they intersected, right? So the separating hyperplane theorem is violated here. So if two convex sets intersect, obviously convex hull intersects, then obviously there is no separation. But this is not an if and only if case also, I am saying. Okay, so what I am saying, so not an if and only if in the sense that if I may have non-convex sets but still linearly separable, that's possible. Okay, but what is guaranteed is that if there are two convex sets non-intersecting, there is a existence of hyperplane. Okay, so but other way is not true. The hyperplane existing does not necessarily imply that two convex sets, two sets must have been convex. Okay, because I can give you another example where a set A is like this, okay, and set B is like this. Now they are linearly separable, right? So hyperplane theorem is not a necessity sufficient. Okay, so I can have a linear separable when A and B are not necessarily convex. Okay, so other way can happen, and but then there is a guarantee that if the convex hull doesn't intersect, there is existence. Okay, so so nevertheless, what we are saying is that realizability assumption covers both. Now how, whether the existence is there or not, in this case I can prove it. Okay, the convex hull is non-intersecting convex side and so on, but here I'm not able to use the separating hyperplane. Okay, so oh wait a second, I can do the convex hull of that also, right? Why not? Is it, so if my argument was all on bound convex hull, then why not do convex hull of this also, right? Okay, so if I do a convex hull, then it will become convex. Okay, and then I can check, okay, whether. So the other part I am not committing right now exactly. So is it true that I necessarily form a convex hull and they should not intersect and there is a guarantee? Okay, is there a counter example where the convex hull will intersect yet there is linear separability? Okay, that I'm not completely sure unless I prove it. Yeah, that's an interesting thing to think over. Okay, there are few cases which are pretty sure. If the convex hull doesn't intersect, certainly there is a linear separability. There is a proof in Boyd. Okay, so separating hyperplane theorem. Boyd convex optimization. So basically the separating hyperplane theorem tells that if two convex sets are non-intersecting, there is the existence of separating hyperplane. We are trying to kind of see the generality of this, right? So we will form a convex hull if they don't intersect, we are done. Here I did a convex hull, it didn't intersect, we are done. Now is there a case where I do a convex hull, convex hulls intersect, but yet without convex hull they are linearly separable? Okay,
There won't be that case.
they won't be, right? Why?
Because
Being made here is that hyperplane necessarily defines half spaces. So these half spaces are necessarily convex, that I agree, and this hyperplane being a superset of the convex hull of this, but this is exactly my point, right? Is there a case where this won't be a superset, like somehow this spills over here?
it must be a superset.
It must be, right?
It,
Okay.
it is convex and it contains A.
It is convex and it contains A, right. Okay, good. Okay, because the convex hull is the smallest possible convex set containing this, so it must have to lie within a larger convex set. Convex hull is the smallest possible convex set. Okay, so I can like write down this. So convex hull is the smallest possible convex set containing those points. Okay, so with this argument it seems it won't be a possibility. Okay, so let us review this. So let us say without doing the convex hull, I have a linear separability. And my question was that does it happen that if I construct a convex hull, there won't be a linear separability? Okay, so the argument here is that once we have that, the one of the half space is a convex set, of course the other half also, and this contained our original set of points. Now if I indeed do a convex hull, it will be the smallest possible convex set containing A. That's the definition of convex hull. So it cannot be containing more points than the half space. It's the hyperplane. Okay, that's a special boundary case. So touching the cases where it touches, we can break the kind of greater than equal to or something like that. It is possible. That's another argument. It is possible that it might touch, but the way half spaces are defined, right? But if it does touches, it will violate again, because if I define half space to be less than, strictly less than this, it is not supposed to touch, right? So it is not supposed to touch basically. If it was touching, it should have been originally touching. Okay. Okay, that's a good discussion going on. Okay, that's right. So so we are more or less settled that separating hyperplane theorem is quite general. Okay. Okay. So and the existence proof, we can have a look. So what realizability assumption is saying that let us assume that happens, but we went one step further and said when it can happen. Okay. Okay. So okay. So so that's a simplest possible classifier you can think of in any machine learning. Now the question is, how do I find this classifier? Okay, so the unknowns in this classifier are W and B. So how do I learn this, right? That's the machine learning part, right? So how do I learn this hyperplane that will classify? So some optimization is needed, like how do I model this problem? Okay, so let us do that. So in this case, we will make use of linear programming. For class of half spaces. So linear programming, we borrow this from the optimization that we did, optimization method, and we recall that that was max of RD and then UW subject to AW greater than equal to V. So we somehow jumped into linear programming, but obviously we have to relate what is going on. Okay, and how does linear programming help in building a classifier? So here obviously W is an as usual we have been using it's a D-dimensional and A is an M by D matrix and V is Rm M dimensional and U is Rd D dimensional. And we jumped into this linear programming, and what we are trying to say is that if we can model this, which we will do, this classification problem as a linear programming problem, then this is a well studied problem. Okay, from in optimization community, they know various ways are there to solve linear programming problem. So in that sense, we are not worried as long as we can model problem like this. So that's what we are trying to do. So let us start from the beginning. So our sample space was x I y I and I equals 1 to m. So there are like m number of samples given to us with labels y I. So this is the training set of size m, right? So training set size is m. Okay, so this modulus means the cardinality of the training set. So since we assume a reliability assumption, right? So since assumed realizability, since we assumed a real eligibility, there will exist a optimal W. Basically, for hyperplane W and B defines the hyperplane. So there will exist that, right? So there will exist there exists a predictor with 0 errors. Okay. So what we are looking for is we have the existence, okay, of a linear classifier, and since there is these samples are linear classifier, then all these kind of the sign of W transpose X must be the actual prediction yi. Okay, so we are looking for W, for which we will have sign of W xi is equal to yi for all I equal 1 to m. Okay, so learning problem is essentially finding a W, and in the W you can involve the B also. Okay, so finding that such that the sign of this W transpose X will be yi. Even if you don't include W, is it necessary to include W? Not necessary, okay, because at the end of the day I am just looking at the angles, okay, because W is this, it doesn't matter where B was, okay, B was giving me this offset where I am, okay. So even if you don't include W, what I am looking for in the sign is just this vector and the corresponding vector which are making acute angle with this, okay. So just W, sign of W is enough, W transpose xi is enough. So this can be cleverly written as follows, okay. So equivalently we have yi which is wxi is greater than 0 for all I equal 1 to m. So it is equivalent, I said, right? So that happens because yi takes values +1 and -1, right? So let us look into this in the cases, right? So if, because yi's are coming from -1 and +1, this is the level set, so it has two possibilities. So if yi is -1, okay, so in that case the prediction of this, so W transpose xi will be negative, okay, that's what we want, right? So in that case wxi is negative, and in this case if I look at yi wxi is positive, okay. So in that case this implies yi wxi is positive, because y is negative, this is negative, multiply positive. The other case is also similar. If yi is positive, then it must be that wxi is positive. In that case also yi wxi is positive, okay. So that's why we can combine it, okay, and we can combine it and say that yi times wxi must be greater than 0 for all the samples. If it's negative, then negative will be positive. If it's positive, then positive will be positive, okay. So that's a clever way to write compactly for both the cases, -1 and +1. Optimal learner will be W star, the weight, which will satisfy this for all I, okay. So that's what we are looking for. We are looking for Wi that does the classification, and doing the classification means this is greater than 0, okay. So we look for so let W star be a vector, let W star satisfies this. and it must exist because of the realizability assumption. Okay, must exist. So it must exist due to the realizability assumptions, and let us define some let us define few things. So define gamma to be a minimum of minimum over I of yi w star xi. I have defined this, I am trying to define this where I am taking the minimum possible I can have. Essentially you can think of, I am looking at the boundary case, right, the worst possible example I, okay, and that will kind of decide the boundary case, right. So hyperplane should be somewhere there. So and then w bar is another new quantity, and let that be defined to be w star by gamma. Okay, so for this let us look at what happens with the w bar, okay, and whether it satisfies some inequality. Look at w star, then I mean the w bar, then so this is for all I. We have yi w bar xi is 1 by gamma yi w star xi greater than equal to 1. Okay. So with this choice of w bar, if we look into yi w bar xi, then in place of w bar we substituted w star by gamma. So we have 1 by gamma and yi, and then we have w star xi. Gamma is minimum of yi w star xi. Since it's the minimum, overall it has to be greater than equal to 1, because if you look into this quantity and this being the minimum of all this, so the denominator is smaller than the numerator, right. So it has to be greater than equal to 1. That's what we use. This is the minimum possible of this, right. So so essentially we have shown that there exists a vector, let us say w bar in this case, for which even greater than equal to 1 is satisfied. Okay. What we are looking for is greater than 0, but what we have shown here is that we can have greater than or equal to 1. Okay. So we have thus shown that there exists a vector that satisfies yi w xi, which is greater than equal to 1 for all I equal 1 to m. Okay. So there is a existence of w, which in this case is w bar, for which we have greater than equal to 1, and such a vector will be obviously a classifier, because we only wanted greater than 0, but we got even greater than 1. Now to find a vector that satisfies this this inequality, we can use linear programming. Okay. So to do the linear programming, we can cleverly define a if we recall a linear programming, then we can, what we have is max of uw and subject to aw is greater than equal to v. So we are if we want to use linear programming, then we are supposed to define these vectors, right. So in this, and our goal is to kind of model this as an optimization problem. Okay, so if we try to model this, then A we can define it in a way that define A to be like this. So the ij entry of A is yi xij, where xij is the jth element of vector, jth element of vector xi. Okay, and v we will define it to be vector of all ones. So v is vector of all ones, right? So we have defined A. So what is exactly A, right? A is yi xij. You can think of this as row by row. Okay, so for all j, let's say I'm looking at the ith sample and I'm multiplying by yi. Okay, and then I want that to be greater than equal to 1 with w also. Okay, so I will explain this in more detail. Basically what I'm trying to say is that the way we are modeling this with A, W and V, it should produce this with this choice of A. Let us look into this. So A, I, J. So the way I want to look into this is like this: xi like this, but then in each of the xi I have yi. So row by row I am adding yi. Okay, so let us say this is 1, and then y2 second sample, and so on, and y m x m, there are m samples. So this is my matrix A, which is m by d, and then we are supposed to multiply this with w. So this is w1, w2, wd, and this is must be greater than equal to v. Now v are all 1. Okay, so we want to produce 1, right? Equation 1. So if I now multiply, right? So if I multiply x1, y1 with the whole w, right? So if I look at the first row of this, so first row of this is indeed y1, x1, w is greater than equal to 1. So this is the first row. Similarly, I have y2, x2, w greater than equal to 1. So this is the second row, and so on. Y m, x m, w greater than equal to 1 is the mth row, and this indeed gives us 1. Okay, so this all this combined, so all this is indeed 1. Okay, so this is exactly what we have modeled 1 as a times w. Okay, so this is this is w, obviously, right? And this whole thing is A times w, and this is our v. Okay, so we have modeled this as A w greater than equal to v. So these kind of things you have to do. Transform your problem into something that is known. Could be LP, QP, QC, QP, cone programming, so many things, right? Semi-definite programming, SDP. So many well-known problems fit in one of these. So in this case, we have done that. We have cleverly modeled AW greater than v. Now the question is, what should we put there, right? Because everything is satisfied by the constraint itself. Constraint satisfy ho gaya, what do I need to do, right? Because only thing I wanted was to satisfy one, and everything is captured by this. There is nothing left for this guy. So you do something dummy there, fool the solver. You take u to be 0, okay, and you provide it to the solver, and let it produce some output for you, okay. So that's what you have to do here. There is nothing in the objective right now, so you put this as some dummy. So so the LP requires a maximization objective LP requires a maximization objective, yet all W that satisfy constraint are equal candidates thus we set a dummy objective which is u is equal to 0. You guys have done SVM. Do you know what SVM does? SVM is a little bit more than this. What does it do? It also does margin maximization. Here we didn't worry about that. So what it will do in the objective is that let us maximize the margin also from the support vectors. Okay, we will do SVM later on. So SVM is essentially an extension of this. It will say that this is my support vector, and this is my support vector, the closest possible here, and you maximize the D. You do this change, and that becomes SVM. Okay, maximum margin linear classifier. You can say like that. But here we are saying that we are happy with any W. That W can be very close to one of the support vector, but as long as it satisfies, it's fine. The SVM is more robust because it's also giving you more margin, and hence a better hyperplane, which keeps a good distance from both, and keeping a good distance from both the classes is good because it will generalize more, because there may be a training data which might spill over a little bit more towards the hyperplane. So SVM kind of will guarantee more generalization in that case. Okay, so that's all with the linear, but we can also develop an iterative algorithm for this, and that's the perceptron view of things. Okay, so we can build an iterative algorithm, meaning so here we have an LP, and we can use some direct solver for LP, because LP has some direct solver. Direct solver means solvers that can give you a solution in very few steps, and then there are iterative methods like gradient descent, where I improve iteratively. Okay, so I will like correct my hyperplane at each time using gradient descent. I will look at the training example and adjust, and finally I will settle on one. So that will be a perceptron view, which is proposed by Rosenblatt. So that's another way to solve this. Perceptron for half spaces. So this was proposed by Rosenblatt. Rosenblatt 1958. The way he proposed this idea is inspired from neurons in the brain. So the way he thinks of this as some computational model that neurons use, and I can go into that as well, but for the moment I will kind of complete this. the learning process, but basically what I'm trying to say is the neuron models are like this. Okay, something goes just like in a neuron, and then some output comes. Okay, this is the motivation behind neural networks. Okay, so it is kind of possible to view everything like that, because W transpose X is a linear combination, right? And then you're taking a sign, right? So that's how he sees things. For us, it's like a hyperplane, W transpose X plus B, but for Rosenblatt, it's like neurons. So X coming from here, and then I do a linear combination with the W. Okay. So in this case, let us say in this 2D, the neuron okay, I don't know why I'm today. Okay, so the neuron model. Okay, I should not use big words today. So X1, X2, this is my X1 and X2, and these are the weights, W2. So in the neuron case, you're saying that you have X1, you have X2, okay, and you do the linear combination X1, W1. So meaning this information comes to the neuron via some connections, and you weight it by W1, and this information comes via another neuron, you weight it, and then you do some activation here, and that will be the sign function, right? So we have also used the sign function, and from here, after the sign function, it will say whether it could be classified as positive class, whether it should be classified as negative class, right? So that's the neuron model of linear classifier. Okay, and that's what Rosenblatt did. So in some sense, his view was slightly general. Okay, because then it can be extended, it can be composed. I can append another neuron, I can have multiple neurons. So that's where you get the neural network idea, deep neural network idea, and so on. So for our purpose, it's one perceptron. One perceptron does linear combination activation, that's it. Okay, so activation here means applying the sign function, but ideally I can apply many other activation function, right? So this is what Rosenblatt did, and then obviously we use build a loss function and do a gradient descent and so on. So perceptron is an iterative algorithm that constructs vectors, W1, W2, and so on. So basically, it's iterative algorithm. So it will construct these W vectors iteratively. W vectors define the plane, right? We are looking for, and so initially, obviously, W1 has to be set to be something. Initially, W1 is, let us say, a set of all zeros. Okay, that's what he did. Okay, set of all zeros. So at iteration t, perceptron finds an example, I where the prediction is wrong. Okay, so where I for which is wrong, let's say. Okay, that's where it will try to update the weight, right? So for which the classification W t xi is not equal to yi. Okay, so the classification is wrong here, then we must do something, right? So then the perceptron updates, then the perceptron updates Wt by adding it to the instance xi scaled by the level yi. Okay, So it's an iterative algorithm. It starts with W1 being all zeros, and at some iteration t, it will find a case example where it will be bad. Okay, if it doesn't find any example where it's bad, then maybe the W learned is already optimal. Okay, so if not, then it will surely find an example where the prediction is wrong. Okay, so it's not predicting the correct level. Then it has to update the current plane, and so plane will be updated by changing the WT, and it does so by adding it to the instance xi, the updates WT plus xi yi. Okay, that's how I will get WT plus 1. So I will write down explicitly what the update is. So the new weight WT plus 1 is WT plus yi xi. Okay, so this is the rule. That's it. Okay, this is the perceptron algorithm. You keep doing this, and if you never get this case, then you know that the current WT is able to classify for all training data. Okay, that's when you will stop. Okay. Now a natural question is this a correct way to update, right? So if I am doing this plus yi xi, why should I do that, right? So let us see what is the effect of doing this. Okay, so let us see. So what we are so remember that our goal when we are doing this is wx is greater than 0, right? So this is what we are looking for, right? We are looking for w which is greater than 0, right? And that w will be the good one for us. Okay, so essentially what we are trying to do is that we want to maximize this as much as possible. Okay, so another way to see this, the perceptron algorithm, is essentially you do gradient descent on this. Okay, gradient ascent, I mean, because it's a maximization problem, right? So it's a maximization problem. So apply gradient ascent. So basically this is about max of, right? So in fact you will recover the gradient like this, I believe. Okay, because if you do the gradient, then you will get xi, because I will take a gradient with wt. So wt will go away and only xi will remain. So this is nothing but gradient descent ascent, and to maximize w transpose x, and yeah, this is it. Okay, so this is gradient ascent, but so we can explicitly say that this is increasing this the value each time. Okay, so for that what we will do is that let us check what t plus 1 did. Okay, did it increase from the previous yi wt x plus 1? Then we know that okay, it is increasing the value, right? So this is xi. Now we put the update wt plus 1 here. So this is wt plus yi xi, wt plus yi xi. Okay, so if we kind of do the algebra a little bit, then we have wt xi and plus norm of xi. So we are now very familiar with these things now. We are doing a lot in this optimization class, right? So that's what we have. So we know that clearly this guy with wt plus 1 is now larger than the original yi xi. Okay, so this is a proof that this is actually increasing the values. Okay, unless your xi's were 0, then you will get stuck. Okay, but if not, then it is certainly increasing these values. So a basic algorithm is like this. Input is the training set, and then initialize. then run the t iteration, then if there is exists an I such that yi wt xi is less than equal to 0, okay, that's the place where misclassification happened, then wt plus 1 is wt plus yi xi as output wt. Okay, so this is a very simple algorithm. You may actually do this. You can try to implement this in Python maybe. Okay, so this algorithm we can prove that it converges. Okay, so we can prove the convergence of this. So this is theorem 9.1, and it says that assume x1 y1 xm ym is separable, okay, meaning linearly separable, and let us define some constant. Let b is min of norm of w such that for all I in M, the sample set M, yi w xi is greater than equal to 1, and let us define another constant r, which is max of I norm xi, then the perceptron algorithm stops after rb square iterations. And when it stops, for all I in M, we do have that yi w t xi is greater than 0, meaning it eventually stops and it does classify. Okay, it learns. There is a guarantee that it learns. Okay, this is what this theorem is trying to say. So let us do the proof of this. Let w star be a vector that achieves the minimum in the definition of B. Okay, so in the B we were defining W which have the minimum possible norm, okay, among for all I and for all I it does classify well. Okay, so apparently this W star is the optimal one. Okay, so because for this W star, obviously the way we have assumed that W star is a vector that satisfies B, so obviously W star is doing this, and since W star is doing this, obviously it's classifying, right? So this implies that yi W star xi is greater than equal to 1 for all I in. So it's not just one W. We have been looking for W which is the minimum possible norm. Okay, that separates. So that is used in the guarantee. Okay, in practice, any W that does the separation is fine. But while we are proving for a guarantee, we needed this W with minimum possible norm. Okay. So let algorithm, the perceptron algorithm runs for t iterations. Okay, that's when like it should stop basically. So basically what we are saying is t is less than rb square. Okay, we have to prove that basically. Okay, so t less than rb square. So the idea of the proof is the following: is that after performing t iterations, the cosine of the angle between w star and wt plus 1 is at least square root of t by rb. So we will try to do that, and doing that, like, what will happen, right? So this is what we will try to do, and if we do that, then it will prove that t is less than rb square. Okay, so let us see this. If we do this, which we are supposed to do, okay, so that is, if we show that the cosine of the angle, which is given by this ratio, w star and t plus 1. So this is the cosine of the angle, right? The way we define the norm, right, we recall that uv is norm u, norm v, and cosine of the theta angle between them, right? So cosine we have found like this: the angle between w star and wt plus 1 is given by this, and we are saying that this must be at least, so it's like greater than or equal to square root of, so this is our plan going on. Okay, so this is square root of t by rb, and if we can prove until here, then by Cauchy-Schwarz, by Cauchy-Schwarz, this guy will be what? Less than or equal to, right? So this is upper bounded by 1. Okay, so we can say this is happening by Cauchy-Schwarz. Okay, and if that happens, then square root of t is obviously less than rb, and this would imply square root of t is less than or equal to rb, and this eventually implies t is less than or equal to rb squared. And if t happens to be less than rb square, and we have said that t is running for, let us say, t iterations, then at most we took rb square iterations, right? And this can happen if the cosine of the angle between w star and wt plus 1 becomes at least this. And if we prove this, then this will conclude the proof. This will conclude the proof. Okay, so this is our plan. Okay, we didn't do anything here. So let us try to prove this. So let us call this some equation number star. Okay, so to show that star holds, we first show that w, the numerator, okay, w star and w t plus 1 inner product is greater than or equal to t. So let us first try to show this. Okay, w star w t plus 1 is greater than or equal to t, and So at the first iteration, we have indeed taken W1 is all zeros in the perceptron algorithm, and therefore this implies W star W1 is obviously 0 to begin with, while at iteration t, if we update using example xi yi, so initially this inner product was 0, but let us see what it happens at t. So W star Wt plus 1 minus, so let us see look at this difference, okay, first. So W star minus Wt is W star Wt plus 1 minus Wt. So this is the inner product, right? So we took the first one common and subtracted the second argument, and then this is W star, and Wt plus 1 minus Wt, according to the update rule, it must be yi x yt, I mean yi xi, right? Yeah. So the update rule, it will be yi xi. So which will be, we can take yi common. So this will be yi W star xi. Now according to what we have assumed, W star is a classifier that satisfies greater than equal to 1. So this quantity is greater than equal to 1, right? So realizability assumption is there. This we started with W star, existence of that. So we have that. Now after performing t iterations, capital T iterations, we get W star Wt plus 1. Okay, let us look into now Wt plus capital T plus 1, and this will be or this could be written as some kind of telescopic sum. So let us see this. So t equals 1 to t, and W star Wt plus 1 minus W star Wt is greater than equal to t. So what happened here, right? I wrote W star Wt plus 1 as a telescopic sum. So telescopic sum is a sum where the endpoints somehow survive. The intermediate one gets cancelled because of the plus and minus, and the endpoint of the first case was anyway 0. So only the last would survive, which would mean that t plus 1 survives. 1 got 0 anyway, and intermediate terms got cancelled. Okay, and so that's how we wrote this as telescopic sum. Okay, but what we have proved just now here is that each of these are greater than equal to 1. So basically each of these is greater than equal to 1, and I am summing them t times. So hence it will be at least t. Okay, so we have this. So we have shown that the numerator, which was our claim, right? So we first saw that, and we did that here, right? So we have shown that the numerator is greater than equal to t. Now let us look into the other part. Okay, so now what we want to show is, next we upper bound Wt plus 1. So next we upper bound norm of wt plus 1, capital T plus 1. Okay, so let us see a bound for this. So for each iteration t, we have norm of wt plus 1 squared is, we can write the update here. So wt plus 1 is wt plus yi xi, and this is, we expand this a plus b whole square form as wt norm squared plus 2 yi w transpose xi plus norm of yi square, we can take common out, and then we have xi norm xi square, and this guy is negative because the I is such that in the perceptron algorithm, right? So I in the algorithm, if you remember, is such that it is a misclassification, right? If it never happens, we are done anyway, right? So we have to assume that at some place there is a misclassification, and the perceptron algorithm tells us that it was the at the tth step there was a misclassification, and it was for the ith sample, and then so I here is arbitrary anyway. Okay, so algorithm is such that yi w transpose xi is less than equal to 0. Okay, so this is why we are saying that this quantity is less than equal to 0, and then norm of xi square will be r square basically, because r was max of xi. If you recall in the theorem, r was max of I norm of xi. Okay, so this was the so r square will be it will be less or greater so at least if I drop this, what I have is this. So I have dropped a negative likely negative term, so at least what I have in hand right now is wt plus yi square norm of xi square. So this we have, and this should be domain, okay, because r is max, right? So the norm of xi square will be lesser than r square. Okay, so this implies norm of xi square will be less than equal to r square. Okay, because r is max of xi, so r square also will be like max of xi square. Okay, so if I take any arbitrary xi, it must be less than equal to r square. So hence we can also write that this is like less than equal to norm of t plus r square. So we got an upper bound. Now if we use this repeatedly, wt plus 1 is less than equal to w t square plus r square, then we will get down to w0, and each time in the recursion we will get 1 r square each time. Okay, so and w0 is basically 0, w1 I mean is 0, the initial guess is 0. So eventually there will be there will be like t plus t of the r squares that will come out, and the last one will be 0 anyway. So eventually this will be t of r square, right? So this will be t of r square. So by recursion and W0 being 0, this implies norm of Wt plus 1 whole square is less than equal to T r squared. So this implies Wt plus 1 is square root of Tr. Norm of Wt plus 1 is less than equal to square root of Tr. And so we have two things. W1, yes, thanks, W1. So we have in the numerator, if you remember, we have some terms in hand, right? So numerator is greater than equal to T we have, and W star is there in the denominator, and W T plus 1 we have upper bounded by sorry, so here also there is a mistake, right? So if we run it for T iterations, yeah, this T is coming from the fact that I ran it for T iterations. Okay, so there is a further thing that I should say, that if I ran it for small t, then it will be small square root of T, right? So the fact that I'm using big T, then this has to be changed to big T. Okay, then I ran for capital T plus 1 iterations, right? Then it will be this. So basically by recursion, for capital T iterations, okay, then we have this. Now we will combine. Okay, so combining this, so let us say this is our A, and combining the one that we got now, let us say this is B, and the fact that, so combining A, B, and the fact that norm of W star is B, we have, so now combining all this, we have the angle Wt plus 1 W star divided by norm of W star W T plus 1, and this is greater than equal to T by B square root of T r, which is square root of T by B r. Okay. So we have shown this, and we from there we knew that T must be less than equal to B square, because we use the Cauchy-Schwarz after this, and then we have T less than equal to B squared, BR squared. Okay. So that's what we were supposed to show, that the iteration runs for at most BR square. Okay. So iteration stops at most before BR square. So that's the proof of that this perceptron algorithm iteratively, if you do, there is a guarantee that it converges. You want to continue, or you want to stop? I mean, this chapter is simple, I guess. I mean, there is next thing is like linear regression, but you already know linear regression, to be frank, to be sure. So what I will say is that read this linear regression on your own, because I have done this several times, right? So they are doing this fitting, right? Line fitting, that's linear regression. So study, okay, just to make sure that we are not very, so linear regression is a very simple thing. Study by yourself, and then also least square. Okay, I have done this actually. I have done this already. That's why it's a repetition for you basically. So 9.2.1 least square, and 9.2.2, which is polynomial regression. That's also I have done. I said, okay, let us take a polynomial. So that's also done. 9.2.2, And okay, what is not done is logistic regression. Okay, so logistic regression I can do. Yeah, that in the next class then, logistic regression. Okay, so for today we will stop, let's say. Okay.